So I'm happy to be here, and let me tell you how I came to tonight's topic. So if you go to a bookstore and you go to the science section, or maybe even the astronomy section or something, you'll find any number of best-selling books that are about, the latest hot topics in astronomy and cosmology. You'll find books about the recent discovery of gravitational waves, which is a really big deal. And you'll find books about the era immediately after the Big Bang that you call inflation. And you'll find books about the discovery of supermassive black holes, millions of times more massive than the sun, and things like this. And all of those books are great. I've even authored a couple of books kind of in that theme. But what I found in giving public lectures and talking to people who aren't professional scientists is that maybe those books are doing a bit of a disservice, because the fact is that without understanding the underpinnings, a couple of levels down from that make up modern science and modern cosmology, these very recent hot topics and discoveries maybe kind of lose their significance. So I'm going to take a couple of steps back, and I'm going to try to tell you the story, the historical story over the last 100 years or so, about how the science of cosmology came to be established. How scientists, against all of their expectations, came to be convinced that the universe is changing, it's getting bigger and more dilute and colder as time goes on. This is an empirical fact, something we've measured beyond any reasonable doubt. And in the past, in the distant past, billions of years ago, the universe was smaller and hotter and much more condensed, much higher density, much more compact. And we call that state, that hot, compact state, the Big Bang. This was a very far-fetched idea 100 years ago. I don't think anyone was taking it seriously as an idea then. But being dragged kicking and screaming, cosmologists and astronomers eventually came to accept this as true because the data is just overwhelming. And I'm going to kind of sketch what that data looks like, what the main discoveries were, and try to explain simple ideas or the foundational ideas to cosmology, like what is expanding space? Even if you think you know the answer to that question, you probably don't. You probably have misconceptions about it. So we're going to try to correct some of those, try to explain some of these basic things, and try to give you a better understanding for why cosmologists think the basic things about the universe that they do. Sound good? All right, so we're going to time travel now to just over about 100 years ago. It's 19 teens, okay? At this point, there literally is no science of cosmology. There's no notion of what the universe is like as a whole. There's no notion of how it might have started. I mean, of course, there are biblical and other sorts of theological notions about this, but science has nothing to say about it. We know that the planet, the Earth, is old. We know it's, hundreds of millions or billions of years old at that point, but we don't know exactly, and we certainly don't know what came before that. We don't know how the Earth came to be formed. We don't know how the sun came to be formed. We don't know how the galaxy came to be formed. In fact, it's more than that. We don't really know there's a galaxy, okay? So we know there's a cluster of stars that we seem to be embedded in, and we called it the Milky Way. That phrase had been coined long before that. But there was an ongoing debate about whether the Milky Way was synonymous, interchangeable with the universe, or whether the Milky Way was one of many things, what we now call galaxies, out there. Like, that was a legitimate scientific debate. People thought that maybe it's kind of like you live on an island and there's water in all directions, and you've never built a boat that could go very far off your island, and you wonder, are there other islands out there? And you literally don't know. And a lot of astronomers imagine the Milky Way was it. We were an island universe and the only island in all of space. And of course, that's a little surprising, because you can take a pretty decent telescope in your backyard, or even a nice pair of binoculars, and you can see other galaxies in the night sky, at least on a really dark night. Maybe not in the Chicago suburbs, but if you went farther out in the country, you could. So why wasn't it obvious to these astronomers that there were other galaxies? Well, here's the trick. So let's say I show you a picture of a big puffy thing, okay? And I say, this is one of two things. Either it's something as big as our galaxy, a very far distance away, Or it's a much smaller cloud of gas and dust and stuff, much closer by. Which is it? Well, just from a picture, you can't tell. They look the same. If I pointed you at the moon and said, is that something a tenth of the size of the Earth and this far away? Or is it something 10 times bigger than the Earth and that far away? It's indistinguishable. You can't tell those things apart. They literally look like they produce the same image. But in the 19-teens and 20s, astronomers developed new techniques to measure not only the size of things, but the distance to things. You start by doing some geometry, and you can kind of measure the distance to the nearby stars. That had been done for a long time. But they developed these other techniques involving these special kinds of stars called Cepheids. And Cepheids turn out to have a brightness that you can predict based on how often they flash. Okay, so the fastest brightening ones had a certain brightness, and the slower flashing ones had a different brightness. So you could work out how bright these stars should be from something other than disconnected from their distance. And now that I know how bright it is, now I can work out how far away it is from me. After all, if I hold a flashlight in the dark out in the distance, you can estimate, based on how bright the flashlight appears to you, how far away the holder of that flashlight must be. So that's what astronomers started to do. And lo and behold, in the 1920s, it became more and more clear that some of those puffy things that you saw with your telescopes weren't small things in our local neighborhood, but they were things much, much farther away, well beyond the boundaries of what we call the Milky Way. And instead, they were things a lot like the Milky Way, outside of the Milky Way, other galaxies, other islands in our universe. And I think that's really the beginning of cosmology. So we started to map out these bigger things. The best example is the Andromeda galaxy, which used to have a different name. We used to call it the Andromeda Nebula. Nebula just means like a big puffy cloud of things. But in the 1920s, it became really clear that the Andromeda galaxy, as we now call it, is a lot like the Milky Way. It's about the same size. It's our nearest neighbor galaxy, but it's not part of the Milky Way. It's outside of the Milky Way. Okay, so now we know that the Milky Way is one of many, presumably many, we now know many, islands in our universe. But we still had no idea of how things got to be that way. We had no idea what the universe was like in the distant past, or what it would be like in the future, how it came to be created. All that stuff was totally off limits to science. We just had no idea whatsoever. But around the same time, something totally outside of cosmology was going on that would give us the tools to address this. And that was Albert Einstein's formulation of the general theory of relativity. This will turn out to be the thing that astronomers needed to start asking questions about how space and time might change in the universe. So give me a show of hands if you have a passing familiarity or more with relativity. Okay, everybody. All right, that's great. Okay, or just about everybody. So I'll give you my own highlights of what I think is so cool about relativity. So the first version, called Special Relativity, that Einstein published in 1905, one of the things that made him famous at that time, showed that space and time aren't the static, immutable things that we normally think about. Instead, distances in space depend on how fast you're moving. How much time passes between events depends on your frame of reference. All of these things kind of turn the notions of space and time on their head. And just to be clear, relativity isn't a speculative hypothesis anymore. It's something we've done, I don't know how many experiments to confirm, but these experiments have been done in so many different ways and with so much precision, and every time they do exactly what Einstein's theory says they should do. Okay? So there's really no scientific doubt that relativity is a good description of nature. Now we expect with any theory that someday it will break down when we measure it well enough, but that has not happened, and we've measured it awfully good. Okay, awfully well. Okay, so moving on, after 1905 in special relativity, Einstein knew this was incomplete. It couldn't be the whole theory. And he had this idea that he would be able to build a bigger theory that included special relativity, but it also allowed one to talk about things that were accelerating and speeding up and slowing down, which special relativity wasn't equipped to do. And he had this thought experiment. He said, okay, imagine you're sealed in a box okay? Like, picture like an elevator car, okay, and it's closed, so you can't see outside of it. And like if you're sitting in a stationary elevator car, you feel like you're being pulled towards one side, what we'd call downward. He says, you know, one of two things is true. Either you're near a planet and, you know, the gravity is pulling you downward, like in a real elevator car. Or maybe that elevator car is accelerating in the direction you'd call up. And you know, if you're in an elevator and you're speeding up, going up, you feel a little heavier. Well, you can kind of mimic the effects of gravity, right? So imagine there's no planet nearby, you're out in space, but you're speeding up, and it's that makes you feel like you're being pulled downward. So how do you hypothetically, Einstein asked, figure out which one is going on? Is this gravity you're feeling, or is this acceleration? Does anyone have any suggestions for how you might try to determine that? Without looking outside the box, that is. Yeah.
Jump.
Jump. How? Okay, so I'm in the elevator. Still can't tell. Feels the same either way.
Compare how fast time is passing relative to someone who's not.
Okay. So the suggestion, so I'm going to repeat things because the online audience. The suggestion is that you compare how long it takes for between two events as measured in the box to someone outside the box. So that is what I call cheating, because I've said you can't look outside the box, which means you can't talk to people outside the box. But you're right, that would work. Okay, so the short answer is there's no way to tell. Okay. And Einstein's insight is the reason you can't tell is because they're actually the same thing. All gravity is, the thing we call the force of gravity, according to Einstein and now according to the scientific consensus, all gravity is the effects of acceleration and geometry of space. So when you look, when you put a bunch of energy in one place at one time, like say the sun, okay? That changes the geometry of all the space around it. It warps or distorts the shape of space-time. And that causes things to accelerate along, their trajectories to change. I'm misspeaking a little bit. If I want to say things really correctly, what the distortion of space-time does is it changes the geometry. So straight lines, what we call a straight line, the shortest distance between two points in space is not what we think of naively as a straight line, but a curve. So the Earth's orbit around the sun is, after the warping of space, the closest thing there is to a straight line. So things move through space in weird ways we call gravity because of the way that energy distorts space and time. So Einstein came up with this equation after many years of work and a lot of going back and forth. And this equation is one of the grandest equations in all physics. It's really hard to manipulate and solve, but conceptually it's really simple. It basically says, on one side of the equation, you put in where all the energy, matter and other stuff is in space. You just describe exactly where it is. Maybe it's all in one point, maybe it's distributed, whatever. You put that on one side of the equation. And then on the other side is the geometry or shape of space and time. So if you have one, you can calculate the other. Okay? So like, for example, I put in, well, there's a star here, and it calculates the size, the shape, geometry of space around the star. And then from that geometry, you can work out what orbits should look like. And they look like the ones we see. Okay? You can do things like black holes with this. You can do things like the deflection of light by gravity. You can do all this stuff, okay? And over and over again, this equation's been shown to be correct. It describes all of the phenomena we're able to measure extremely well. So what does this have to do with cosmology? So in, I think it was 1917, Einstein said, okay, well, I've already calculated the orbits of planets, calculated the deflection of light, I've calculated a few other things all using my equation. Let me see what happens if I just put in the whole universe on one side of the equation. Okay? So he did some really simple approximations, which turned out to be pretty fair approximations, but he didn't really know whether they'd be. He said, let's just imagine there's kind of a uniform abundance of matter everywhere. Okay, so if you look at the universe in a big enough scale, there's kind of the same number of atoms or whatever else per cubic meter on average everywhere. It's not perfect, but basically you can assume it's homogeneous and you can do some approximations. And then from that, he works on the other side what the shape or geometry of space is. And here's the weird thing he found. The thing he hated this. He did not want this answer, but it's staring him right in the face, is it wasn't a stable solution. Okay, so if I take a high school physics problem, and so for example, let's say I write down the equations of motion for this glass. Okay, I say, well, there's this mass here. Here's the various forces on it, whatever, and if I let it go, what's going to happen? Well, it's not going to be stable. It's going to fall downward. There's no solution in which this floats, okay, at least not without some other thing acting on it. And what Einstein found is there was no solution in which the universe just stayed fixed if it was filled with homogeneous matter. Depending on how much matter, the universe would either expand or contract as time went on. So like I said, I need to explain what that means, because almost everybody thinks they have some idea what it means, and they're almost always wrong. Okay? It's pretty subtle. Okay? So what we mean when we say space is expanding, and we now know it's expanding, it's not contracting, but at the time, both were viable solutions. When we say that space is expanding, what we mean is if you take any 2 points in space, point A and point B, and you wait longer, the distance between those 2 points in space will be greater than it was at that previous time. So every 2 points in space get more separated as time goes on. That's all we mean by expanding space. So here's the analogy I like to give. Okay. So the Earth, let's say you're on a globe, and the radius of the Earth is growing with time. Okay. Just imagine that. Here I am in Chicago, and from Chicago, I get in a really tall building, so I don't have to worry about the curvature of the Earth. And I look over and I take a look to Detroit, okay? Well, if the radius of the Earth is expanding, then the distance between me and Detroit, Chicago and Detroit, is getting bigger as time goes on. It would look like Detroit's moving away from me, okay? So astronomers have ways to measure speeds of things, okay, if they're going fast enough. And so you can look at distant galaxies and see what their speeds are like. And yeah, they're all moving away from us, all but a few really nearby ones. But basically, other than those, which are just kind of moving in random directions, the distant ones are all, without exception, moving away from us. That's because space is expanding between us and them. Furthermore, now let's say I look at Detroit and it's moving at 100 miles an hour away from me or something, whatever, some number. And then I look to New York. Well, there's more distance between me and New York. So it's going to be moving away even faster, proportional to its distance. So I measure the New York galaxy, and it's moving 300 miles an hour away from me. Then I do it with London, and it's 1,000 miles an hour, et cetera. The farther away the object is, the faster it's moving away from me. That's what expanding space looks like. So like I said, Einstein hated this idea. He just seemed to think in his gut that the universe needs to be static. It shouldn't be expanding, it shouldn't be contracting. He just thought it was patently absurd. He looked up in the night sky and things seemed to be the same as astronomers 1,000 years ago said things looked, and pretty much that seems true. What Einstein didn't appreciate is all the changes that were going on were just so far away that you just don't see them with the night sky very easily. You have to have very powerful telescopes and notice these sorts of changes. So Einstein looked at the math and said, okay, what do I have to do to this math to make it static, okay? And I said before, there's one side of the equation is where all the stuff is, and the other side of the equation is the geometry. Well, Einstein said, well, I'm gonna add a third term. This third term we called the cosmological term. It's mathematically allowed. There was no reason to include it other than it's not wrong. You can do it, but there's nothing about the universe that says it should be there, but you can write it down, it's allowed. And he could tune it just right and make the universe be stable. It's kind of like, so like I said before, there's no static solution where this thing just hovers. But he said, well, I'm going to put this anti-gravity in. And it's going to push up just the right amount to hold this steady. If it was a little lower, it would fall. And if a little higher, it would fly upward. But if I put it just right, I can make it hover. Okay? That's what Einstein did to save the universe from expanding or contracting, or so we thought. But here's the problem. It didn't work. He didn't admit this for a long time. The universe isn't homogeneous. Some places have a little more matter than other places. And what would really happen is those places with a little more matter would contract, and those places with a little less would expand. And it wouldn't be static. It would be like you have a bunch of different glasses. This one might be static, but this one would fly up, and this one would fall down. And that would be our universe. It would be full of places where falling up and falling down, or contracting and expanding. And Einstein, this was pointed out by other people working on the theory, but Einstein was so famous and everything that no one really listened to him. And for years, basically, people took Einstein at his word. And that all changed in, I want to say it's 1927 or 1928. I'm a little fuzzy on some of the dates. But an astronomer who went to the University of Chicago, actually, so a local guy named Edwin Hubble, was out measuring galaxies, and he measured enough of them, including their distances and velocities. And he found a particular relationship. Okay, so for each galaxy, he plotted how far away it is from us versus how fast it's moving away from us. And there was some scatter and stuff, but more or less, he found something that looked like that. It looked proportional to each other. So now think back to my Chicago, Detroit, New York thing, okay? The world's getting bigger. Things nearby us, like Detroit, look like they're going away from us at a certain speed. So like something like this might be Detroit. But then New York is moving a lot faster, and London's moving faster still, etc. That's what Hubble measured. In effect, he measured that the universe is expanding, at least our piece of it, okay? Eventually, within a couple of years, Einstein accepted this was true. He called his cosmological term that he had added by hand a big blunder. He said it was the biggest blunder of his life, at least by some reports. And the scientific community more or less got behind this conclusion. The universe seemed to be expanding. So we had gone in about a 15-year window of time from not even knowing if there were other galaxies to knowing that there are a lot of them. Our universe is full of these things. We now know that there are hundreds of millions of galaxies in the observable universe. And they're all flying apart from each other at extremely high speeds. Okay. So that's phase one of our history of cosmology. And it's already 7:30, so we're going to have to speed up a little bit now. Any questions before I move on? Okay. Yes?
What exactly is the universe moving into?
Oh, excellent question. So to repeat it for our internet audience, if space is expanding, what's it expanding into? I'm going to paraphrase it that way. So everyone asks that question, and they consistently, I've heard it many, many, many times. If you're asking it, it means you're not thinking about the question right. Okay? And you're not at all alone. Everybody falls for this, okay? If there was something that space could be moving into, what would we call that stuff?
Another dimension.
I'd just call it space, okay? And, you know, so I mean, you could call it other space or whatever, but that's the wrong way to think about it. Space isn't moving into anything. The distance between 2 points in space is just getting bigger. If you want a different way to think about it, just imagine that everything in space is shrinking. It's the same thing, works exactly the same way. So let me explain. So what's this room, maybe 70 feet from side to side? So let's say I've got my 12-inch ruler. I lay them side by side, take 70 of them to go from one side to the other. And then I wait, and I do the measurement again. Now it takes 80 of my rulers So I conclude one of two things. Either the room's growing or my ruler's shrinking. Can't tell them apart. Okay? So if you struggle with like what's going on, how's the space getting bigger, what's it moving into, just is perfectly fine to substitute that idea with all of the stuff, all the ways we measure distances in space are getting smaller. That works just as well. But it's weird because that means things like the speed of light is getting slower, because that's one of the ways, that's one of our rulers. Okay? It means the size of atoms is getting smaller and at the same rate. And a bunch of other things are getting smaller. So all this stuff has to get smaller in unison. That's why physicists don't really think that's the correct interpretation. But if it helps you think about it, I sometimes use that as like a thought trick. Okay, so let's think now about what it means for space to be expanding. In particular, let's think about what it means about the universe's past. Okay, so as far as we know, there's no way to create or destroy matter. Or, well, okay, that's not completely true. For the most part, the amount of matter stays pretty fixed. Okay, that is true. So if space is getting bigger, if the volume of any piece of space is growing, what does that mean about the density of space, the density of matter in that space? It's decreasing, right? You're diluting space. So if the distance between these 2 points in space double, that means the cube here gets 8 times bigger, and the density in that cube gets 8 times smaller. So that means if I go back far enough in time, everything was more dense. Okay. And if you think back to, like, say, high school chemistry, you know that if you take like a gas of particles or something, or gas of atoms, whatever, molecules, and you squeeze it, it gets hotter, right? You can heat gas up by compressing it. So people started to realize that if space is expanding, then things were denser and hotter in the past. Okay. And if you just take Einstein's equations and say space is expanding and just run those equations backwards, turns out that in some billions of years, we now would say 13.8 billion, but back then they didn't know exactly, but some billions of years in the past, you would not only reach a point that was very hot and very dense, but you'd reach a point that was infinitely hot and infinitely dense, a finite time ago. At that point, all of the equations just like kind of break down. They don't make any sense. There wasn't, you can't even talk about time before that point. In a very real sense, time comes into existence and kind of unravels with space at the singular point 13.8 billion years ago or so. We call this the Big Bang. And sometimes people refer to that individual singularity as a Big Bang. Sometimes people talk about the Big Bang just to mean that kind of hot, dense state in the first hundreds of thousands of years or something. So people use the phrase to mean both of those things. So sometimes that's confusing. So people started to recognize that this was a possibility. And some people thought it was more than a possibility, but it was starting to be contemplated in the 30s and 40s mostly. And but there was another way of thinking about it, which was actually more mainstream and more like respectable astronomers advocated for a different point of view. The most famous example is this British guy named Fred Hoyle, who's by all accounts a very, very serious astronomer, very, very famous guy. And he hated the idea of the Big Bang. He just thought that was ridiculous. And he said, no, there's another way to explain all this. He just said that as space was expanding, more matter was being created as well. At a very slow rate, it doesn't take very much. But every once in a while, a new proton pops into existence. And we've never seen anything like that, but it might be going on. And if you had that sort of situation, you could have the same density at all times. And this could have been going on forever. Okay? You can't tell. So that was called the steady state theory. And that was kind of the mainstream idea. And then there were these other kind of like oddball cosmologists pushing for the Big Bang. This was a big debate for a long time. And ultimately, it's not a debate you could settle with philosophy or words. You had to go out and measure stuff. And slowly, certain types of astronomers, namely like radio astronomers, started to notice that the number of galaxies really, really long ago per volume was different than it is now. So the universe seems to be evolving to some extent. So it doesn't seem like we're in a total steady state anyway. So that gave some credence to the Big Bang. But the thing that really helped was that the Big Bang guys started to argue that they could explain the abundances of things like hydrogen and helium and other sorts of chemical elements in the universe by arguing they were formed in the Big Bang. Okay? So think about what goes on in the core of a star, like the sun. The sun gets its power through nuclear fission. They take hydrogen nuclei, they fuse them together to make helium, and that releases some energy. Well, you know, in the core of the sun, you're at some millions of degrees Kelvin. And if you went back far enough in time, the universe was it. The whole universe, all of it, was at millions of degrees Kelvin. That should have been going on then too, they argued. And they thought they could calculate how that should play out. So in the 40s and 50s, people started to do these calculations. And they worked out that you could explain all of the helium in the universe, which is something you couldn't do with stars and other things. There's no way to explain how much helium we had with those things. So it really seemed like the Big Bang provided a solution to this outstanding problem. So that kind of elevated a little bit more. And furthermore, they said, well, but if you're going to make all the helium that we see in the universe, then there has to be a bunch of radiation left over from this too. What I mean by radiation is just light, a background of light. Okay? But the light would be so cold that we wouldn't even notice it. It would barely be detectable. But then in 1964, two astronomers, they were working for the company Bell Labs, and they had a radio antenna in New Jersey. And they were going to use it to try to measure radio waves from the Milky Way galaxy. But to do that, you had to get all your backgrounds really low. You need a really, really clean antenna. They couldn't get this damn hum to go away. It just all the time. And they didn't know anything about the Big Bang. They didn't know that there was supposed to be a hum. But they were detecting and they couldn't explain it. And after months and months of trying different things and getting frustrated and not being able to get their experiment to work, one or both of them, I forget, made a drive up to Princeton where they started to ask people questions like, what could this be? What's going on? And they met some cosmologists there, and they're like, that's the thing we've been writing about. That's how you prove the universe began in a Big Bang. And they're like, I don't know, we're just some radio astronomers. Like, that seems really far-fetched. So they wrote a paper which just said, there's this thing, we can't make it go away. And in the final paragraph, there's like one sentence saying, one of the suggestions is that maybe this has something to do with cosmology, Big Bang stuff, whatever. One little sentence. And then right after that, those Princeton guys wrote another paper saying, Big Bang, this is the Big Bang. And in the years that followed, people started to measure, as a lot of people measured it. They measured better and better and better. And man, it looked just like the thing that they had predicted. Okay? And by that I mean it's nearly a perfect black body spectrum. A black body is just something that's a perfect radiator, something that's in total equilibrium and radiates light as if it were sitting there just communicating perfect with itself forever. Okay? And that's what the early universe basically did. If I plot this, it looks something like this. So this is the frequency of the light. And this is the intensity of the light. And a black body spectrum looks kind of like that. Okay, it's just this curve. You learn to calculate this sort of curve, and freshman or sophomore physics as a physics student. It's totally understood. It's completely theoretically predictable, and they measured, and it's exactly like that curve. It's perfect. Okay. In fact, in the early 90s, they sent the first satellite into space to measure it, and they showed a plot like this. So I didn't know about it at the time, but some years later, I saw somebody give a talk on this, and they showed a plot. It looked just like that. And they said, this is what the theory prediction is. And now we're going to overlay the error bars. Okay, so like a normal error bar and a normal talk has some curve, and there are measurements like this, right? And like these are the uncertainties in each measurement. But in this case, they said, now we're going to overlay the error bars. Click. And nothing happens. The error bars are so small, they get lost in that line. And then he said, I'm going to make the error bars 10 times bigger. Click. Still can't see them. Now I'm going to make them 100 times bigger. Now, okay, now the line starts to get a little bit bigger. Okay, that's how good this measurement, that's how perfect this black body is. It's exactly what the theory predicts. That more than anything else convinced the astronomical community that the Big Bang's real and the universe some billions of years ago was in a very hot, dense state. And I think it's totally undeniable. But then it gets better. So from there, cosmologists start not just measuring that shape, but they start measuring it more and more and more precisely. So that's the average spectrum that I plotted there. Turns out that you can calculate that there should be some places in the universe that were just slightly hotter than other places. On average, it's about 2.7 degrees above absolute zero. But some places will be 1 part in 100,000 hotter, and some parts will be 1 part in 100,000 colder, things like that. And we've measured that. We've measured it really, really precisely. We have these beautiful maps, and they subtract off the average, and you just see the patterns of hot and cold spots. And when you start to analyze that, you can work out not only that there was a Big Bang, but precisely how the universe expanded from that Big Bang, and exactly how much matter it took in the universe to explain it, exactly what the shape and geometry of the universe is. All of these sorts of things that they could have only dreamed of in the middle of the century, we've now measured so precisely and just amazingly. And it just keeps falling back to exactly what the theory predicts it should look like. We're still waiting for the theory to break. Everyone thought it would break long ago, and it just keeps holding up. Now, okay, maybe I'm not telling you the whole story with that, because there are new things we've had to introduce into the theory to make sense of the data. Most of the matter in the universe isn't made of atoms. It's made of stuff we call dark matter. That's sort of my research specialty. But we know how to put dark matter into the theory, and we do that, and it fixes a lot of problems. Okay, so we're pretty sure dark matter exists. And it turns out the universe is not only expanding, but expanding at a faster and faster rate. At least it has been over the last few billion years. And to do this, you need to reintroduce something kind of like Einstein's old cosmological term. The version that we need now doesn't balance things like this glass of water, but it just kind of tosses everything upwards. Okay? And that's okay. We can do that. It's a little surprising. We weren't expecting it, but we know how to do that. And if you include those two elements, then the whole theory holds together beautifully. Now just let me make a couple of sociological statements, okay? Because I think these are sometimes important. When I watch the news or read articles in the press about science, what I often wish they would report is, to what extent is the thing you're talking about in this article or in this story consensus or just someone's opinion? It's really hard to tell, right? Everything I've told you tonight is total, utter consensus. I literally don't know a single professional cosmologist who disagree with anything I've said tonight, unless I've just misspoken by some accident or something. But if so, that was just an honest mistake. Everyone agrees that 13.8 billion years ago, the universe was compact and hot and expanding. And they agree that this light that was detected in the 60s and scrutinized ever since was generated in that period of time. They agree that the vast majority of the helium in the universe today was formed in the first handful of minutes after the Big Bang. They agree the universe is expanding and expanding faster today than it used to be. Actually, that's a point that I can at least think of one cosmologist who disagrees. But it's one out of maybe a couple of thousand that I know. Okay, so we'll still call that a consensus. We live in something we like to call the age of precision cosmology. And I think it's really earned that title. There is very, very little room left for debate. Now, there's tons of room for debate about what happens at the very beginning. The first fraction of a second, we don't really understand that at all. Some weird stuff has to have happened then. That is totally open to revision. It would not surprise me at all if textbooks in 2067 tell a totally different story about the first second after the Big Bang. Maybe they won't even talk about it in those terms. I don't know. But I would say everything from about a minute after the Big Bang on, there's very little room for that to change. It's basically how we've mapped it out. All right, so I mentioned that there's these patterns of hot and cold spots in the sky. These places that are 1 in 100,000 times hotter and places that are 1 in 100,000 times colder. And you can compare those patterns to what the theory says. Turns out there's one little patch about the size of the moon on the sky that's pretty cold, and a cold spot that big, there's only like a 1% chance or something that there should be one of those on the sky. So maybe that's just chance. Sometimes 1 in 100 things happen. Or maybe it tells us something about the initial conditions of the universe, something about the way things started out that was a little unexpected. And then this connects to this thing called inflation, which is this hypothetical era right after the Big Bang where things expanded super, super fast and left the universe very changed. And it turns out that you can explain this cold spot without resorting to small probabilities if you imagine certain kinds of inflationary scenarios, which would lead to the formation of not just one universe, but many, many, many universes. A practically infinite, let's say, number of universes. Now, I'm pretty open-minded to that. It would surprise me if ours is the only universe. And OK, I should say it kind of depends what you mean by that, too. After all, there's a certain volume of space that things can reach us traveling at the speed of light. Anything farther away from us than that, we're totally disconnected from. We can never communicate with it, and it can never communicate with us, even hypothetically. So I'm willing to say that everything in that sphere, everything in that radius is a universe. Obviously, there's stuff beyond that, right? So that just means that if space continues, and I have every reason to think it does, those are a bunch of universes. Now, are there other universes that don't even connect to us in that way? Yeah, I don't know, but very possibly. That doesn't surprise me at all. I would, at one point, people were wondering whether the sun was the only star, and it wasn't. People used to wonder whether the Earth was the only planet. They wouldn't have used the word planet because they were calling the other things out in the sky as planets. But the only big chunk of rock that you could walk on, and it wasn't. People, like I said in the beginning of this talk, people used to wonder if the Milky Way was the only galaxy. So I think we tend to default to the idea that the thing we know might be the only one, and I tend to think that's usually not likely. So I'm totally open-minded to the idea that there are any number of universes.
It looks like there's a question from somebody watching through the internet. Okay. If all matter was in a hot, dense, singular state, how did it overcome the force of gravity? Is there any evidence from the studies of supermassive black holes that help explain how it could have happened?
So if you take Einstein's equations and you say, well, there's homogeneous distribution of matter, turns out that the rate at which space expands is larger if there's more stuff in it. Okay? It's a little bit counterintuitive, but the thing we call like the Hubble constant, which is really how we talk about the expansion rate, that squared goes like the density of stuff in space. So in the early universe, when there's a lot of stuff in space, the universe actually expanded really quickly. Okay? So So it's a little counterintuitive that you would think that if everything's really dense, it would stop it from expanding, but that's not how it actually works. It turns out that gravity doesn't work that way. It has more to do with the geometry of space and time, and how these things interplay. So if I can plot something for you. The relative size of the universe, by which I mean the distance between 2 points in space relative to the distance now, okay, did something like this. Okay, so it was, the slope here is pretty steep. That means things were growing fast. And now things are growing slower, but recently, like I said, things have started to accelerate. So there's an uptick now. Okay, so this is approximately the history of our universe to date. Now, people wonder, if we just extrapolate, this is going to keep going up and our universe is going to start expanding really, really fast in the future. But we really don't know that. Weirder things have happened in the past. Maybe other sort of stuff will happen. We really are just speculating when we talk about that. We don't really understand the cosmological term that's driving this. So I'm open-minded, but a naive extrapolation says that will keep going fast. But the point to answer this question is back here, these equations somewhat counterintuitively say that when you have a very, very, very dense state, you'll expand fast, not slowly, or not backwards. Now, the connection to black holes, if in most theories we have about how inflation worked and stuff, very few, if any, black holes were formed in the early universe. Those would have been the sort of things that formed later. But there are weirder theories, special inflationary theories, where you can form a lot of black holes in the beginning, and maybe those can make up some of the dark matter, for example. But those aren't typical inflation theories. Those are out of the ordinary, I would just say. They're a possibility, though. This is the sort of thing people write papers on.
Have they identified the nature or the type of subatomic particles that make up the dark matter, the cold or the hot dark matter?
No. That's the short answer is no. That's what I try to do. Okay, I hypothesize new subatomic particles that might hypothetically make up the dark matter, and I propose tests that we can conduct observations or experiments to narrow the range, and maybe one day observe something that we call a discovery and say, oh, now we know what the dark matter is made of. But so far, none of this has been conclusive. We ruled out a ton of our best ideas. So if you asked me 15 years ago, what are the odds? And you said these experiments are gonna be done, and they're gonna be successful in the sense that they're gonna be as sensitive as we hope they'll be. What are the odds that those experiments will be sensitive enough to tell us what dark matter is made of? I said, oh, really good, 90-something%. I would have been really enthusiastic. Maybe I would have said 80%, but something like some pretty big number. And it hasn't happened. These experiments have been conducted. We've done the Large Hadron Collider, which is the world's biggest particle accelerator today. They haven't seen any evidence of dark matter yet. We've done this string of underground experiments. Those, I really would have bet a lot of money would have seen dark matter, and they haven't. There is one signal that's been reported that very well might be dark matter, but it's not far from conclusive. And we're seeing an excess of gamma rays from the center of the Milky Way. And it's possible that's being made by dark matter. I'm sort of a big proponent of that hypothesis, or that interpretation in my field, but a lot of my colleagues disagree. So just for complete fairness, that is not a consensus view at all. But with the exception of that possibility, we just haven't seen any evidence of the particles that make up dark matter. We just feel it through its gravity, and that's the only reason we really know it's there.
Could you say something about science and its compatibility or incompatibility with spiritual practice? And if you want to, do you consider yourself to have a spiritual practice, and how does your knowledge of science affect that?
Okay, that's a fair question. I happen to be an atheist. I don't ascribe to I'm a strict materialist. I don't see any reason to hypothesize anything that couldn't hypothetically be described by the scientific method. Okay. That being said, many of my colleagues who are just as smart as I am and know just as much science as I do have a different view on that. So they certainly think it's compatible, and I mean, my reflections upon the universe don't give me any reason to invoke a spiritual hypothesis, but other people find that hypothesis is something they're drawn to. And I'm not going to really second guess that. I'll have a respectful debate with them. But it's clearly compatible in the sense that some people who really do know a lot about science find themselves having theistic attitudes. Personally, that doesn't work for me. I don't find those arguments compelling, but I respect it.
Could you go into a little bit about the Higgs boson and what the significance of that is? Sure.
So this is the biggest deal in science in the last 20 years or something. Okay. It's a little subtle and a little hard to conceptually explain, but I've got a few tricks that I can kind of get close to. So it turns out that, well, okay, I'm going to go back. This is going to be a long answer. All right. So there are four forces we know of in nature. There's a gravitational force, the electromagnetic force, the strong nuclear force, and the weak nuclear force. At a particle level, at a quantum level, we don't understand how gravity works. Okay, so I'm just going to throw that one aside and talk about the other three. The other three work at a quantum level because by exchanging a particle through space. So take the electromagnetic force. The electromagnetic force exists because of the particle we call the photon, the quanta of light. So I'm going to go over here. If I put my hand out and fall, I stop, right? Why? You think it's obvious, but it's not at all obvious. My hand is mostly empty space. There are a few atoms here and there, but the volume of those atoms is tiny compared to the size of my hand, and that wall is mostly empty space. So why don't my atoms just fit through the atoms in the wall? Does anyone know? Because the electrons in my hand and the electrons in that wall are throwing photons back and forth. And those photons push against each other. They transfer momentum, okay? And the photons talking back and forth between those electrons is what we call the electromagnetic force. It's the same thing that drives static electricity, okay? All right? So the reason this force exists is that charged particles, electrically charged particles like electrons, radiate these photons. They create these photons, and that force exists because of their electric charge and the photons that talk to that electric charge. In the strong nuclear force, that's the thing that holds protons and neutrons together, and nuclei and the quarks and stuff. That's brought into effect not through a photon, but through something else we call a gluon. It's a lot like a photon, but it's more strongly interacting, and it works in really short distances. And then the third force is called the weak nuclear force. And it's different than the others. It has particles associated with it too. We call it the W and the Z bosons. They were discovered in the 80s. But whereas the photon and the gluon have no mass, they're exactly massless, which means they always travel at exactly the speed of light. The W and the Z bosons are heavy. It turns out the mathematics of these kinds of equations only make sense if the particles are massless. And people knew this in the 50s and 60s. And they had all this evidence that these W and Z bosons are probably heavy. Does that mean our theory is totally destroyed and totally nonsensical? It's illogical. It leads to a bunch of things you'd like to calculate that will turn out to be infinity, or things that you calculate in two different ways and you get two totally different answers for what you should measure. Things like that. So it looked like a really sick theory. But then a group of particle theorists in the 60s worked out a way to kind of save the massive W and Z bosons from this logical inconsistency. It's called, we now call it the Higgs mechanism after Peter Higgs, this Scottish physicist who was responsible, him among a few others. And basically the idea is that there's this field that fills all of space. Okay? It's everywhere, it surrounds all of space all the time. And when certain particles interact with that field, these particles that otherwise would have been massless basically slow down and start acting like they carry a lot of energy with them. In other words, they act like they have a mass. Okay, so these W and Z bosons, they really are massless in some sense, but they interact with the Higgs boson that makes them act like they have a mass. So we say that the W and Z acquire their masses through interacting with the Higgs field. Good. Also things like the electron, its mass comes from interacting with the Higgs field too. Most particles that have a mass fundamentally do get it from the Higgs. But that was just a theory, okay? That was in the mid-60s this was originally suggested. We didn't have any experimental evidence of this until 2012, when for the first time we created and observed Higgs bosons directly at the Large Hadron Collider. So Large Hadron Collider is this, I'm going to get some of the numbers wrong, but I think it's a 17-mile circumference ring underneath the city of Geneva and the surrounding countryside in France. Around this ring, we have giant magnets that shoot protons around them at nearly speed of light. I think it's something like 99.99999997% of the speed of light, if I got that right. It's pretty close to that, if not right. And so some of them are going clockwise and some go counterclockwise, and then at designated places the beams are crossed. And 600 million times a second, these protons collide. And in those collisions, we put so much energy in one place at one time that we can use Einstein's equation equals mc squared to take that energy and make new kinds of matter with a lot of mass. And the Higgs boson's a heavy particle. This is the quanta that make up the Higgs field. We can make these individual particles. And we successfully did it. For a long time, theorists worked out what these particles should look like, and it looks exactly like that. It's amazing how much it looks like the thing that had been long predicted. So the Nobel Prizes were awarded and all this, and we can put a big feather in our hat. But we're really not happy with how things are right now. We built this machine not just to discover the Higgs boson, but to discover a bunch of stuff we were way less confident in. Okay, so we were pretty sure the Higgs was there. But we hoped a bunch of other stuff would be there too. And the other stuff hasn't shown up yet. We're still cautiously optimistic that any day now, the new particles will start to fly out of the machine. But so far, no discoveries other than the Higgs have been made. But keep tuned, stay tuned. That's my long answer.
Okay.
Will we ever have technology to exit the solar system and go through wormholes?
Well, so I don't know about wormholes, okay, but the solar system, yeah, sure we will. That's not even that long off. You might see the day that we have the technology to send people outside of our solar system. In fact, not people, but we've, for the first time, just very recently sent a thing outside of the solar system. The Voyager probe, just a few years ago, left the boundary of the solar system for the first time. It's the first time we've ever sent anything man-made out of the solar system. Now, it's a lot harder to put people on something that's going to go that far. But people are really talking seriously about putting manned missions or missions with people on to Mars. And from there, it's just a hop, skip, and a jump to the edge of the solar system, right? So yeah, that's going to happen. Now, wormholes are another thing. We don't really know whether wormholes exist. It's the sort of thing that the math says could exist. We've never seen one. So, maybe they exist, maybe they don't. We're not sure about that.
When I first learned about the expanding universe, one of the frightening notions was that it was all coming to an end. And I'm wondering, in the acknowledgement of the potential for multiple universes or something in the first few seconds or before the first minute, is there some thought or calculation, or those who are working on a solution to the idea, like Einstein, he wants it static, sustainable, and to see beyond the event horizon, or to find the event horizon within the entire spectrum of multiple dimensions.
So, I mean, I'm personally not worried about whether the universe will be in good shape in a trillion years. You know, I don't have that kind of horizon to worry about, okay? I know some people find it really disturbing that the universe might end one day, okay? I don't. I'm fine with it. I take some comfort in the idea that there might be, you know, practically infinite number of universes out there, and they're all, you know, there's everything possible exists somewhere. I find that pleasant, I guess. So in terms of our patch of space and its future, though, if I go over to that plot and I just take a naive extrapolation, and this keeps going faster and faster, I'll describe to you how this plays out. Well, the faster the universe expands, the stuff that's the farthest away from us that we can see right now, we stop being able to see it, right? So if these 2 points in space are moving away from each other faster than the speed of light, light can't get from here to here anymore. So that means there's a circle around us, a horizon. And the faster space expands, the smaller that horizon gets. So we start getting blinded. In galaxies that we used to be able to see, we can't see anymore, okay? And so as we climb up that hill, the horizon gets closer and closer and closer, and eventually, you know, this is a very, very long time in the future. I don't even know, but like it's impossibly far in the future. But you reach a point where you can't see outside of the Milky Way. All the other galaxies disappear from the night sky. And then some other impossibly long period of time later, after that, the Milky Way starts being kind of torn apart by the expansion of space. And then you can only see our solar system. Actually, by then, the solar system will be long destroyed, but some other solar system that people have traveled to by then and colonized. And then, you know, the planets start getting pulled away because space is expanding between the various planets and its host star so fast that all that gets torn apart. And then in the very end, every atom is by itself and pulled away from all other atoms. And then the subatomic particles. So the very end game is individual particles existing, never encountering another particle. Nothing ever happens. So that's a pretty boring universe in the end. I encourage you not to let it bother you. It certainly doesn't bother me.
I'd like to ask a question myself. Is there still any viability in the theory of expansion and contraction of the universe, so that it's a cyclical process?
So the vast majority of cosmologists think that's really unlikely, okay, that the universe is going through some sort of expansion and contraction in a cyclic way. But not everybody, okay? So there's this really highly respected, famous guy at Princeton, Paul Steinhardt, for example. And he really thinks that's a very likely answer. And he's worked on this a lot, and other people have worked on it. So it's not considered crazy. It's in bounds, okay? It's like it's in the scientific purview. I was going to say mainstream, but that's maybe not quite true. It's not quite mainstream, but it's not considered crazy, okay? Like good, smart, knowledgeable, you know, mentally stable people are working on this, okay? So it's not out of bounds, but it is a minority position, is what I would say, but one that serious people are actively considering.
You mentioned your, if I'm not misspeaking, materialist, complete materialist. What are your thoughts regarding consciousness in that context? So
I have no particularly compelling reason to think consciousness is anything other than an emergent phenomena that comes from a whole lot of interplaying atoms in my brain or your brain or whatever. I think it requires a great deal of complexity, but I think that's exactly what my brain facilitates. And I have every confidence that the sort of processes that go on in my brain or yours are things that we can build, at least hypothetically, with ordinary materials. I think the differences between what goes on in my laptop and in my brain are more a matter of scale than of kind.
What's the theory for why the relative size is suddenly expanding so rapidly?
The uptick?
Yeah.
Yeah. So think back to the Einstein's effort to make things static. So he said, well, this thing equals this thing plus this other thing that I'm just going to put in by hand. Turns out that what we had expected when we did this wasn't this. We expected that. Okay. So to make this uptick happen, we had to put in that term, that same kind of term that Einstein had. It has a different number out front of it, so it's a different size of the term, but the same kind of term. We call this, in modern times, we call this stuff dark energy. Okay? Conceptually, you can think of dark energy as follows. So we talked about matter and expanding space and how it gets diluted, right? Well, dark energy is a kind of energy in space that doesn't get diluted. So when I take a cubic meter of space and say I have 1 unit of dark energy in it, and now I double its volume. If it were matter, now I would have a density that's half as much as it used to be, but not with dark energy. You just get twice as much dark energy in the same density. So it seems to be a fixed energy density that comes with space. And if anyone tells you they understand why space comes with that, they don't know what they're talking about. We don't have any idea. When we try to calculate this stuff, we don't get anything like the right answer. We're totally at an utter loss to explain dark energy. We just measure it's there. And maybe one day we'll be able to explain it, but not today.
So it was measured that all the galaxies, I guess, near ours are being drawn to a singular point, and I said, I was wondering if there's any theories on what that great attractor might be.
Oh, okay.
For like Laniakea.
Yeah, so I'm not sure there's all that much to be made of this, right? Okay, so the universe isn't completely homogeneous. There are some big chunks of matter out there, over densities, and this is one of them. But I don't think it's any more special than that. It's kind of like, Asia's a big continent. But I don't think there's anything magical about it. It's just, a place with a lot of matter happens to be one place, some people have made a bigger deal out of it than I am right now. But yeah, that's all, basically how I see it.
This idea of non-diluted dark energy, is there a relationship between dark matter and dark energy and the Higgs field that you're talking about?
So people have written papers on this sort of thing. Personally, I don't see any reason to speculate that dark matter and dark energy are connected in any obvious way. For the most part, dark energy seems to be something having to do with the quantum nature of space. I don't know what, the calculations don't come out, but it doesn't seem to be, a typical kind of matter, okay? Whereas dark matter, like just some sort of hypothetical subatomic particle that's in some sort of gas and it doesn't interact very much, it will do everything you want dark matter to do. That's really easy for a particle physicist to write down a theory that does that. I don't know how many times I've written down one, and many of my colleagues have written down their own theories of what dark matter could be. We can make sense of dark matter. We might not know which of our guesses is the right one, but I can write down any number of pretty good guesses. Dark energy, we don't have any of these guesses. None that are very attractive anyway.
And the Higgs field, is that related to that?
Well, in some of the dark matter theories, some of them anyway, the Higgs interacts with the dark matter, and some they're related in the theories. Like, for example, there's a very, very popular particle physics theory called supersymmetry. And in supersymmetry, there's not just a Higgs boson, but there's something called the Higgsinos. And those Higgsinos could be the dark matter. So in some of these theories, they're really deeply connected. In others, not so much. So like I said, the problem with dark matter isn't coming up with a theory. It's that we can come up with a lot of good theories, and we're not sure which ones are right.
Growing up, I remember studying in physics that gravity was the attraction of different masses to one another. Is that still the case?
Well, it's a pretty convenient way to look at it, but it's an approximation. Okay, so you're describing Newtonian gravity. So according to the Newtonian universal law of gravitation, the force between any two bodies in gravity is proportional to their masses and inversely proportional to the square of the distance between them. Okay, like they still teach that. It's not wrong, but it is an approximation. So as long as you're not talking about a very, very, very strong gravity, it works really well. But for example, if you tried to calculate very precisely what Mercury's orbit should be using that, you get it just slightly wrong, measurably, but slightly wrong. To get it right, you need to use Einstein's equations, which in most cases, are indistinguishable from the Newtonian equation. But in cases where you have a really strong gravitational field like Mercury or black holes or anything like that, then you need the full relativistic treatment. So philosophically, we don't think any of our theories are true in the sense that they're never going to be shown to fail. We imagine, or at least I imagine, that every theory is an approximation of something even more true, but some theories are really useful or indistinguishable from true. And right now, as far as we know, general relativity is indistinguishable from true. We haven't found anywhere that it fails yet. We're pretty sure it will fail someday, but it hasn't yet. Newton's theory is really useful, but Einstein's is more useful.
So this is my last question for the evening. Can you comment, after everything that you've talked about with the Big Bang, about this theory that came out, or maybe it's a hypothesis in the early 1990s, that we're living in a hologram, that the cosmos that we live in is a hologram?
Yeah. So let me say what people mean by a hologram in this context. So a hologram is something that let's say an n-dimensional space, like our three-dimensional universe, or three or four including time, can be described on something with n minus some other numbers of dimensions, okay? So maybe the reality in some more fundamental way isn't three-dimensional, but it's two-dimensional. And you can encode 3 dimensions worth of information somehow onto a two-dimensional surface. It turns out that mathematically you can sometimes do this in certain physical systems. One reason why physicists got really excited about this comes from the field of string theory and people thinking about black holes. Turns out it doesn't really make sense to talk about what's inside a black hole. The amount of information, or entropy is what they would say, but really I prefer to think of it information. The amount of information in a black hole is proportional to its surface area. That's pretty weird, right? You'd think it's its volume, right? If I asked how much information is contained in this cube of gas, and I pick some other cube of gas and it's twice as big, I'd say, well, it should scale with volume, but not with black holes. When you get to these really strongly gravitational systems, it's what we call its Schwarzschild radius or event horizon. That surface defines its information content. So people started to think, well, this is like a seemingly three-dimensional thing, but all of its information is encoded on a two-dimensional surface, and maybe that's true with the universe too. And we just we don't see it that way. So there's no one out there saying that the universe is a hologram, and we know that to be true. What people are doing is they're saying in some of our best theories, these very, very hypothetical, unproven, but serious theories, in some of those, something holographic seems to come out sometimes. And maybe that has something to do with reality. So that's kind of the state of things. I would say that something like that is approximately the current thinking. And I don't know how we go from where we are now to the answer on that. There's a big gap between speculating about that and knowing it to be true.
It's becoming pretty common recently to discover new planets using gravitational wobble and all that. That's really for far out planets. But they've been discovering things recently within our solar system that might be within the Kuiper Belt or possibly right around or outside the Kuiper Belt. So is the Kuiper Belt still seen as the last thing in the solar system, or is that expanding now?
So first of all, like, you're right, extrasolar planets, like outside of our solar system, I remember when the first one was discovered, and now I don't know how many thousands they're up to, but like it's really exploded. Okay, that's a brand new thing, it's awesome. We're actually doing statistics of extrasolar planets now. We're starting to get to the point where we can measure like their chemical compositions and things. We can start to see, you know, what's the chemistry in these atmospheres like. It's pretty great. Now, going back to our solar system, different people mean different things by the boundary of our solar system. Like before I talked about the Voyager probe leaving the solar system, what I meant by that specifically is they're leaving the volume that's influenced by the magnetic field and solar wind of the sun. So the solar wind that kind of blows up a bubble, and there's like a bubble where if you pass through that, suddenly the cosmic rays and the environmental factors suddenly change as you kind of exit that boundary. So that's well beyond the Kuiper Belt and stuff. There's probably somebody who's maybe they're watching right now, who's like a solar system astronomer who's like, no, that's the wrong way to think about it. You should really think, I don't know. I don't study that stuff. There are probably different definitions depending on which field you're working in. But you're right that our very notion of the objects that are in our solar system have transformed. You know, the famous Pluto thing was part of it. But what happened is it just turns out there are a whole lot of things like Pluto. And either we have to call all of them planets or none of them. And we decided it's easier to subtract Pluto than to add 30 or 40 or 50 other new things. So we're discovering there are a bunch of Pluto-like planetoids and dwarf planets and things like this. And out there in the Oort cloud and out in the Kuiper Belt, there's probably a whole lot of stuff we don't know about, including like people talk about this thing Planet X, which, I mean, it's probably real, I guess. I don't really know. I mean, but it seems pretty likely to be a real thing. And it's not small. It's gargantuan. It's way out there, though. But yeah, so there's a lot to figure out, even in our own backyard.
What is a black hole?
Good. So if you take a chunk of matter, doesn't matter what, and I'm going to squeeze it down to a really small size. If you put enough stuff in a small enough amount of size, the gravity it will create is so strong that even light can't escape away from it. So if I just, with the Earth's gravity, I take a baseball and I throw it up, okay, even a fastest major league pitcher in the world can't make that baseball escape the Earth's gravity. It's going to fall back down to Earth, okay? So they can maybe throw it 100, 105 miles an hour. If they threw it faster, it could go even higher. And if you could throw it at about 11 meters per second, okay, way faster than anyone can throw a baseball, it would actually go off forever. It would escape the Earth. That would exceed the escape velocity of the Earth. But now, imagine I took the Earth and I started squeezing it down, started shrinking it down. As you do that, you make the escape velocity go up. It gets hard because it's more contracted and more compact, the gravity's stronger, and it's harder to get that baseball to escape. Turns out that if you squeezed it down to about a size of 3 centimeters, the whole Earth, the escape velocity would be about the speed of light. And that means that nothing, even light, which is the speed limit of nature, the absolute speed limit, then nothing can get away from it. So there's around that 3 centimeter object, so you picture like a ping pong ball as heavy as the Earth. That's going to be surrounded by this boundary that nothing can go into or out of. And we call that thing a black hole. Now, the first black holes were discovered late 60s, I think, maybe early 70s, around then. No, 70s. And these were objects that used to be ordinary stars, but exploded as supernova and left behind a big black hole. And since then, we've discovered that there are a lot of other much bigger black holes, supermassive black holes. Like in the middle of our galaxy, at the center of our galaxies, there's one a few million times as massive as the sun. There are some black holes out there that are roughly 1 billion solar masses in mass. So there are all kinds of black holes, and they're pretty common. Just a year or so ago, we discovered for the first time that evidence that black holes, big 30-ish solar mass black holes, were merging. We discovered the ripples in space-time we call gravitational waves that merging black holes could make. So we're learning new things about black holes all the time.